Here we're going to look at two very basic yet important concept problems. Let's take a look at the first one. Alright, this is the question. Figure 1, or a figure I'm going to draw it later, shows a person with mass small m standing on a platform with mass big M. The person is holding one end of a cord that's wrapped around a frictionless pulley and connected to a platform. The cord and pulley have negligible masses compared to the person and the platform. Okay, before we dive into the problems, let's first visualize this. So right now we have a pulley up here, so we have to have a ceiling and a pulley at one, and then there's a cord on the pulley, wrapped around the pulley. At one end of the cord we have a platform. I'm going to draw a triangle. This is the platform and these are the strings that's sustaining it. And on the other end we have a person holding on to the cord. Okay. Then let's look again at what the problem is asking us. Number 1, find the least amount of force the person needs to exert on a cord to keep the entire system in equilibrium. And what is the maximum mass the platform can have? Okay, let's just focus on question 1 first. Question 2, we'll be looking at it in the next lecture. Alright, so here is where the 3 steps to analyze forces come in. Step 1, choose the appropriate object. Step 2, analyze the force and draw a free body diagram. Step 3, analyze the result of the forces and list the mathematical equation. Remember that in the previous lecture we said that you must analyze all the objects. So what are the objects in this problem? Let's take a look at the diagram again. Over here again. Well, there are the person and the platform. So it's only the person right here and the platform. Here, since assessing a problem, the cord and the pulley have negligible masses, meaning that they're massless, we're going to ignore them. That leaves us with only the person and the platform. Alright, back to first step. Choose the appropriate object. Let's first choose the person. So here, let's give you a fresh page. Let's write step 1. Analyze, or I'm going to write that clear, analyze person. Of course, once you get familiar with these steps, you don't really have to write them down anymore. But for the present, I suggest you to write down every single word in the steps so that it sticks to your brain. Okay, step 2, analyze the force and draw a free body diagram. Alright, let's look at this problem again by redrawing it over here. We have the ceiling, the pulley, the cord around it, and we have the platform. And let's make this longer, and the person pulling on to the other end. Okay. Alright, what are the forces? First, start with the act at a distance forces, and that's gravitational force. Since the person has a mass of small m, hence he or she experiences a force mg pointing downward. So right here, experience a force right here, small mg. Okay, next the contact forces. Contact forces only occur when there are contacts. Alright, so what is the person in contact with? The cord and the platform, right? Okay, so the person is in contact with the cord and the platform. The person is in contact with the cord, so there is a tension force right here pointing upward. We call it T. Next, the person is in contact with the platform. So right here, I'm going to use orange. Platform, so it experiences a normal force pointing upward, which is N. Okay. Alright, so the person is in contact with the cord and the platform. What else is the person in contact with? No, nothing more. You might say maybe it's in contact with the air. No, we're gonna ignore air and any buoyant forces because the forces are so small, they're negligible. So this is how we complete step 2. You first find equidistant forces, and then you look at the contact forces. What objects are in contact with a person? Well, in this case, the cord is in contact with a person, so there is a tension force. I'm going to write it right here. Tension force. Actually, we start with the equidistant forces first, so I'm going to write mg. And the next one is the tension force. And the next one is the normal force when it contacts with the platform. Now let's move on to step 3. Step 3, it says to analyze the result of the forces and list the mathematical equation. Well, in the first question, let's see back here, it says that the entire system is in equilibrium. So, is anything moving? No, everything stays stationary. We conclude that this is a static equilibrium problem. The mathematical equation are as follows. The first one is we say that the sum of all forces is equal to 0. So basically the forces pointing upward, which we have right here is T, pointing upward, plus N, all the forces pointing upward equals to the forces pointing downward, which is mg in this case. So T plus N equals mg. That's how you get a static equilibrium. So this is how you solve the problem using the 3 steps in analyzing forces. Step 1, choose the appropriate object. Step 2, analyze the force and draw a free body diagram. And step 3, analyze the result of the forces and list the mathematical equation. Are we finished it? No, we still have to analyze the platform. Remember, we have to analyze all the objects. Alright, so we had to analyze person. Now we're going to analyze the platform. Alright, same steps as before. Let's get the first page right here. Step 1, write this down for the first time, analyze platform. And then step 2, find all the forces. Now let's redraw a diagram. When you're actually solving the problem, you don't really have to draw so many diagrams again and again. All you have to do is just draw on the problem it has. The diagram that the problem provides, but just for clarity, I'm drawing them all again. Okay, so let's look at now we're looking at the platform, not the person, the platform. What are the objects that the platform is in contact with? So, the other end of the cord, right? So it's in contact with the other end of the cord, so we have a tension here, T. Alright. Here comes the question. Why is the string tension also T? Why didn't we call that the one before we called T1 and call this T2? Why is it the same as the string tension as the person is pulling on? Why is it all T's in both cases? Well, we're going to save this for the next lecture. Actually, it's not that hard. If you pause and think about it for a moment, I believe you can get it. Here's a hint. What happens if the tension at both ends of the string is different? So you have a piece of string or a piece of cord. What if you tug it at different T's? What would happen? Okay. For right now, all we have to know is that tension is the same for all parts of the same string or cord. If you ignore the weight of the cord, then tension is the same for all places along the same cord. That's why we said that the tension is T over here and over here. Okay, next, what else is the platform in contact with? The platform is in contact with the person standing on it, right? So right here, this is person. So it's experiencing a normal force. Right here, it's pointing downward. Okay. Oh, well, before that, we should also mention that the platform also experiences equidistant forces, which I forgot to mention in the first place, and it's big mg. Okay, so, and then we have a normal force right here. I'm going to write it right here. So we have the equidistant forces, which is the gravitational force, big mg, N, and the tension force T right here. Alright, let's first look at this normal force right here. So this is what we're going to talk about. Some of you asked that, why isn't the person exerting the force mg on the platform? If the person is standing on the platform, why isn't it pointing downward and let's say small mg. Well, this is the reason. The person is not putting his or her entire weight on the platform. In fact, the force between the person and the platform is only the normal force in. The person did not put his or her entire weight on the platform because the cord right here is sustaining part of that force. That's why we don't put the mg over here. So we don't talk about the mg. In fact, if you look at it, here's a really cool thing. If you look at this end, and back to this end over here, this is actually an example of Newton's third law of motion, action and reaction. If the person exerts a force in on the platform, then the platform will exert a force that has the same magnitude but opposite direction force on the person, which is this end right here. Even though we haven't actually this end right here, because this is the platform exerting on the person, while this one is the person exerting on the platform. Okay, even though we haven't introduced Newton's third law of motion formally, we'll be using them when solving problems. So the end the platform experiences and the force in the person experiences right here is actually Newton's third law of motion, action and reaction. Alright, let's move on to step 3. We're not finished with it yet. Step 3. Analyze the result of the forces and list the mathematical equation. This platform is also stationary. So for the mathematical equation, we set the forces pointing upward equal to the forces pointing downward. For upward, we have only T. Downward, we have big mg plus n. So this is the second equation. So to sum it up, we have two equations right now. The first one, from analyzing the person, we have T plus N equals small mg. And the second one, from analyzing the platform, we have T equals big mg plus N. Here we want to solve how much force the person should put on the cord to keep the entire system stationary. Well, let's put these two equations together first. So the first one is N plus T equals small mg. And the second equation is T equals big mg plus N. Alright, right now, so how much force the person should pull on the cord to keep the entire system stationary? Well, the amount of the force that the person needs to exert is this tension right here, this tension T right here. So let's solve T using these two equations. All you have to do is do your algebra. So I'm gonna move this n over here. That gives me T equals small mg minus n. And just copy the other one. T equals big mg plus n. Then I add the two equations together. I get right here 2t equals big M plus small m, and the entire thing multiplies by g. I move the 2 over right there. It's a t equals to m plus m divided by 2, and the entire thing multiplies by g. Okay, this is your answer. Well, you might think it's quite complicated at first, but once you get used to the 3 steps, and once you get really familiar with them, they can become a second nature. Then you will be solving problems like this in no time. You look for the objects, so you look for the objects you want to analyze, and those are the right here, the person in the platform. Then you analyze each of the objects individually. So you analyze the person right here, and you analyze the platform right here. You find all the forces acting on it and list the mathematical equations. Then, in the last step, you solve the equations to find what you want using simple algebra. Now you have the basics down. I'm going to show you how to solve using a faster method by looking at the entire thing as a system. Alright, so step 1, we're not just analyzing a person or a platform right now. What we're going to do now is analyze person and platform. Remember in previous lectures we said that you have to analyze all the objects, but you don't have to analyze them individually. You can look at all the objects as one single system and then just analyze that system. You'll see how simple it can get. Alright, so I'm going to draw the diagram again. Alright, I think I do this. So we have a platform right here, and then a person holding on to the string this way. Okay. Alright, so right now we're looking at both the person and the platform as one single system. I'm going to draw a big red circle right here as one single system. Okay. Step 2. What are the forces exerting on it? I'm going to write step 2 right here. What are the forces exerting on it? Let's first start with the add the distance forces. So if you add the weight of the platform and the weight of the person together, you get, I'm going to write right here, it's a little bit hard, that's called big M plus small m multiplies by G. Or just big mg plus small mg, but I'm going to simplify it like this, in this way. Next, you try to find the contact forces. Well, the system is in contact with the cords, so you have a tension T right here, and you have another tension T right here. So the system is experiencing two tension forces pointing upward and one gravitational force pointing downward. So write it right here. Okay, because we're regarding both the person and the platform as one system, whatever the person and the platform is in contact with is also what the entire system is in contact with. Well, you might be asking, what about the normal force right here? Right? Let's go back. This normal force right here. What about this normal force? Why aren't you including the normal force right here? Well, the normal force, if you look back in this circle, it's within the circle, so it's within the system, and it's actually an internal force. It's the force acting between the person and the platform. And if you look at the system as a whole, we ignore the internal forces. Okay? So, next thing, we look at step 3. The entire system is in stationary, or you can say it's in static equilibrium. The sum of all forces should equal to 0. Or you can simply say that the forces pointing upward, which in this case is one T and another T, equals to the forces pointing downward, which is big M plus small m multiplies by G. You put these two T's together, you can get 2T equals that. And then you were solving for T, remember? So we move 2 over and you get the same answer right here. Check it for yourself. Same answers, like right here. So to sum it up, in the first method, we've listed 2 equations. In the second method, we listed only 1 equation. And if you look at them carefully, they are the same equation. So this equation right here, I'm going to underline it right here, is the same one you get right here. So that's why in earlier lectures I said to, go back, that's why I said in the earlier lectures, I said to first look for the appropriate objects. Appropriate is the key word. If you choose a good one, you reach the final answer faster. If you choose a bad one, well, as long as you follow the 3 steps, you'll still reach the final answer. Don't get me wrong, it's just that you might take a bit more time reaching the correct answer. You'll still get there, but you might spend more time than necessary. As for the first question, let's look at an alteration of the first question. So back here, the second question of the first question, it says, what is the maximum mass the platform can have? Okay, well, we haven't really considered the maximum mass the platform can have when we were calculating question 1. We were simply solving for the tension T. Well, should there be a limit as to how heavy the platform can be? When we were analyzing the person, we have the equation T plus N equals small mg. Since N is positive, we know that N is positive because we are certain that the normal force is pointing this way, or in this case pointing upward. If N were negative, then that meant we had the direction backwards. But anyways, back to the equation. So if N is T and small mg are all positive, then we know that T must be lesser or equal to small mg. If we say that that T is greater than small mg, what do you think would have happened? Take a look at the diagram. If this T over here is greater than this mg over here, then the person would be pulled upward. Hence, T should always be less or equal to mg. The tension force T from our previous calculation, it showed that T equals. Okay, so what we're going to do right now is going to replace that. So we have T, I'm going to use another color, so T is less or equal to mg. So we replace that into saying big M plus small m divided by 2g is less or equal to mg. If you do all the algebra, you would get, right here, I'm going to write it in pink, is big M is always smaller or equal to small m. If you actually think about it, it's pretty reasonable. If the mass of the platform equals to the mass of the person, then no one is moving. The entire system remains at equilibrium. However, if the mass of the platform is actually heavier than the mass of the person, then the person will be pulled upward. So the answer is pretty reasonable. Tension should not be greater than the weight of the person. That's all for this lecture. In the next lecture, we'll be looking at the second question of this problem.